Welcome to the channel. It has been a while since I've recorded on this channel, not because I've forgotten about it, but because I've been nervous, unsure what to talk about, and in the end, I always open all my videos with complete transparency. I am not a teacher. I'm barely a student because I dropped out of high school over 30 years ago, so I am self-taught. I'm reading books now for the first time in my life. I've already gone through about 5 or 6 books, predominantly all in astrophysics, but I go beyond just astrophysics, like Neil deGrasse Tyson, for example, would do, or Brian Cox, or any of those great people. I like to talk about anything like I did in my last video. How was the Grand Canyon formed? I could talk about animal behavior. Why do tornadoes turn clockwise in, the northern hemisphere, but counterclockwise in the southern hemisphere? Or is it the other way around? Anyhow, anything that has to do with the universe, a little bit more expanded beyond just space and astrophysics, although that being predominantly the main highlight of what I do like to talk about. So anyhow, here we go. This is, as I've said before, this is more of a learn with me. This is definitely not me teaching you, because I don't have the right to call myself a teacher with barely a grade 9 education. Okay, so absolute zero. What is it? First, I want to say this. Basically, if we want to go on the extreme, which we're not going to get too much into, look at how many numbers are there here. Okay, let me just zoom that in over my bald pumpkin head. That is roughly the hottest the universe allows, physics allows, in Celsius and in Fahrenheit. Okay, it's a pretty big number. But when it comes to being the coldest, we actually can't go that low. And what is cold, really? Temperature isn't just how cold something is, it's how much energy the atoms have, right? So when something is super hot, the atoms are going to go really, really fast. And when they're cold, they're going to slow down. They're almost going to become motionless as you approach absolute zero, which is why the Kelvin scale is used, because Kelvin is based on physics, Celsius is based on water, and Fahrenheit is based on human experience. And in case I forget, yeah, see right here. To elaborate a little bit more on Fahrenheit, because most people that are going to watch my channel and this video are going to be familiar with Fahrenheit, and potentially they want to know where it came from. It had to do with a scientist whose last name was Fahrenheit, Gabriel Fahrenheit, I think. Super cold salt mixture. He was playing around with that, and it ended up being 0 Fahrenheit. Then he talked about the human body temperature, roughly between 96 and 98 Fahrenheit. And then water freezes at 32 Fahrenheit, whereas water boiling is at 212 Fahrenheit, and that's a 180-degree difference right there. And that divides nicely, which helps for precise calculations and whatnot. And each degree is going to be smaller than Celsius, so you actually get finer detail. Okay, so those are the 3 reasons why we use that. Water freezes at 0 Celsius. For the lack of a better term, atoms freeze, not cold freeze, but like motionless practically in time at 0 Kelvin, which is why it's called absolute zero, because nothing can go below that. This is not like time dilation, though, where everything is motionless. Like if you were to watch as an observer somebody crossing the event horizon of a black hole, that's time dilation. This is atom dilation. No, that was a joke. That does not exist. I made that up. I was trying to be funny. Ha ha ha. Okay, so the colder something gets, the slower everything moves, aka sloth mode. Here's where it gets crazy. There's a temperature called absolute zero, as I've said, 0 Kelvin. That is minus 273 Celsius, or practically minus 460. But to be super precise, it's minus 459.67 Fahrenheit. And it's at this point that atoms are practically motionless. There's practically no motion left in them, but they are still technically moving. So, and here's the twist. You can actually never really reach absolute zero. Physics says that you can get closer and closer, but you can never actually hit that true blue absolute zero. The coldest natural place in the universe, which brings me back to this thing, is the Boomerang Nebula. I'm going to show you a couple of pictures here. This one was taken from NASA. The two of them were taken from NASA. This was in 1998, I believe, and this was roughly 2023. This one looks just more blue. This one is more like a rainbow, and I will explain why they look so different in just a moment. Okay, so now let's leave Earth and go into the deep space. The average temperature of the universe is about 2.7 Kelvin. Okay? Or minus 270 Celsius, minus 454 Fahrenheit. And that's from the leftover energy after the Big Bang. Okay? But there's one place that beats even that, and again, that's the Boomerang Nebula. And the nebula is at about 1 Kelvin. That's colder than space itself. How, you may wonder? It's expanding insanely fast, and that expansion sucks energy out of the gas, cooling it down to near absolute zero. It's basically the universe's natural freezer. The coldest temperature ever made by humans. Now, this is where humans get really wild. Scientists on Earth have created temperatures even colder than space, the average of space. We're talking about a trillionth of a degree above, just that small, above absolute zero. At these temperatures, something insane happens. The atoms stop acting like individual particles, and they start behaving like one giant wave. This is the state that is called the Bose-Einstein condensate. Scientists used a combination of lasers and magnets, to trap and cool the atoms down to almost absolute zero. First, the lasers slow down the atoms. Then the magnet fields hold them in place. Finally, the hottest atoms are removed, leaving behind the ultra-cold cloud. And it's at that point the atoms stop acting like individual particles and merge into a single quantum state called the Bose-Einstein condensate, as I just said. So, everyday cold, this is me showing you why are we using Kelvin. Well, because the numbers are smaller, for one, but because it shows something really, really interesting. So, let's say we go from minus 30 degrees Celsius, aka minus 22 Fahrenheit. And we're just going to drop it down a couple of degrees to minus 32 Celsius, or minus 25 Fahrenheit. It's just a couple of degrees. Numerically, it's just a couple of numbers, right? And on the Kelvin scale, that's going from 243 Kelvin to 241. It's just a 2-degree drop. That's a drop of 0.8% when you're using the Kelvin scale from total energy. Basically, not really noticeable whatsoever. But when we get closer to absolute zero, say we were to go from minus 271 Celsius to minus 273 Celsius, or minus 455 to minus 459, well, that's going from 2 Kelvin to 0. That's now a 100% drop. You're almost removing the entire remaining energy in life, in the universe. So that's why it's a lot more dramatic. That's why we use the Kelvin scales for physics. Okay? Now I'm just going to brush up on... I was going to explain really quick, kind of off topic, but not really, as to why these pictures look different. So the old picture from 1998 is closer to a single filter or slightly processed image. It shows a faint glow, limited color because less data combined, less aggressive processing. This is closer, kinda, not really, to what your eyes would actually see, what it would perceive, but this is by far much brighter than what you would actually see. It would be much more like grayish blue, and it wouldn't nearly be as bright, okay? But it's just to showcase it, right? The newer image is built from multiple wavelengths of light. So the colors are assigned to different energy levels or elements, right? It includes details your eyes can't detect. Just like, and I hope I don't get this wrong, just like when you look into the night sky, the reason you don't see the nebula and why some cameras for astrophysics, astro cameras or whatever they're called, they're able to stretch out time. It's recorded over a lot of time, and then it condenses all that light. Bam! And you're able to see it. Well, your eyes can't do that. I think this is a similar thing. But it includes, like I said, details your eyes can't see. This is not what it looks like. This is what's physically happening translated into color. Okay? Just in case you're like, oh, wow, it looks like a rainbow. No, it does not look like that. Just like when you look at pictures of the black hole with that big, bright, orangey, white, beigeish kind of, color. That's not what it would actually look like if you saw one. They're actually a lot more creepy than that. You would actually barely see much unless it was actively feeding, and then you would see some light part. Anyways, that's another story for another day. I think I've covered everything. This wasn't supposed to be like a university level, right? I just wanted to explain a little bit what's the coldest, versus the hottest. Because you could think, oh, we could go super hot. We could go super cold. No, you could go a lot hotter than you can go colder. Yeah. And like I said, that's a massive number, right? No matter if it's Celsius or Fahrenheit versus just minus 270 or minus 450 something. It's a much smaller number. And I thought that was interesting. And then the whole thing with the Kelvin and why we use the Kelvin, to me, it made complete sense. Why it's used for physics and not used for temperature. Whereas Fahrenheit is actually better for the human experience of temperature. It's more precise. Especially in the US, even though it wasn't originally intended for this, it actually scales better from 0 to 100 Fahrenheit, in which, for the most part, the US can reach those temperatures. It just makes it better. But logically speaking, the vast majority of the world has agreed upon that Celsius tends to be, for the lack of a better term, a better measurement. I really enjoyed making this video. I myself have learned a lot making this video, because when I was researching and piecing together all of the information for me to read off of, I knew I wasn't going to have all of this memorized, which is the difference between a real teacher and obviously somebody like me that's just reading off his own notes, is they would just have that in their head. You ever seen Neil deGrasse Tyson have to reference a book? He just looks right at the interviewer or whoever he's speaking with, and he's just, right? All that information comes out. I need my notepad to do that, because it's not fully embedded in here, but I have picked up a lot over the couple of months that I have been getting into this. And like I said, it's just, for me, it's just super exciting. I've always been drawn to numbers and math and all that sort of stuff. Most things that most people wouldn't care about, I care about the most. It's just the way that it is. A thumbs up, as always, if you did happen to like the video. It does greatly help support the channel with the algorithm in trying to make me a little bit more relevant in the search results when people are looking shit up online. And if you didn't like the video, go ahead, give it a thumbs down. I'll bend it in half and twist it and break it off where the sun don't shine. I'm just kidding. And if you want to subscribe to the channel, naturally, that would be great. But if not, thanks for stopping by anyways. Take care, and if I'm lucky, maybe I'll see some of you in the next one. And to help me out, for the 3 or 4 people that are subscribed to my channel, and maybe the 2 people that'll see this video, let me know down below in the comment section if you have a topic of something that you would like me to research. Even if I know nothing about it, I will extensively research it, and I will try to sound half competent when I make my video on said topic. Take care. Bye for now.